Morning, everyone. Today, the first speaker will be Perez-Mato professor, and his talk will be magnetic space group versus irreducible representation and the Beer-Bell Crystallographic survey. Welcome.
Thank you. Thank you. I think during these days you have seen a lot of equations, a lot of formulas, and yesterday a lot of things about irreducible representations and magnetic space groups at the beginning. And probably you don't have understood much because in a few hours you cannot just get a full book of group theory. So I'm going to try in this talk not to put a lot of formulas, but try to give you what I think is most important. In principle, you are going to use all the time computer tools and programs. And what you have to know is what the program can give you, what you can ask to the program, and to understand what is the output of these programs, okay? So the first thing is just a reminder of, I think, what you should already know, that magnetic ordering is a symmetry breaking process where the symmetry of your system changes between the paramagnetic phase and the magnetic phase. And so you have a group-subgroup relation between the two phases, between the two symmetries. And the point we have not stressed until now is that if you lose operations, you lose symmetry operations that before kept the system invariant. Now that you are in a lower symmetry, these symmetry operations that have been lost will take your system and will produce another system, okay? So if you have lost some kind of space group operation from the paramagnetic phase, it means that if you take your structure, we say that your structure is distorted with respect to the high symmetry phase, to the parent phase, to the paramagnetic phase, and now you apply your lost operation, and what you will get is another distortion, not the one that the system has, but a different one. In fact, this is what we call the domains, okay? The domains are just related one with the other just by a lost operation that was present in the high symmetry phase. So, and what is the relation between these two distortions that you obtain when you apply a lost operation? It is described by what we call a representation of the group of the high symmetry group. That means of the one of the paramagnetic phase. So any magnetic ordering, in principle, is described by a distortion. And this distortion just transforms by the operations of the high symmetry phase as a representation, by means of a representation. And this representation, in principle, you have seen yesterday, representations of a group can be reducible or irreducible. Let me just show this in a cartoon, okay? So here you have your structure described by your spins and your atomic positions. Now you apply an operation of the parent space group, and what happens is that you obtain a different you distinguish the two structures, because the two structures, this symmetry in general, some of them will be kept and you will not see any difference, but some are lost, and then you will see the difference between the transformed structure and the original one. And how do you describe this transformation? This transformation, I mean, if I put this mathematically, the most simple thing would be just to indicate the magnetic moment or the spin of atom 1 along X, the component along Y, along Z, of one atom, of another atom, of another atom. And so I have 3n parameters in the end to determine any magnetic ordering in my structure, if I have n atoms in my structure. N in a crystal is infinite, okay? So, but let's take it, this n, as some big number. So, the point is that when you apply this transformation, you can describe it mathematically as a matrix 3n by 3n, okay? Everybody understand that, okay? You start with your set of spins, you apply the transformation, the atoms do not move because you are applying, the atoms will be exactly in the same position, so you will not distinguish the positions because you are applying an operation which was part of the parent space group, which fulfilled that the atomic positions do not change. But you have taken the spins and you have just put the spin of one atom in another atom and rotate it as an axial vector and applying time reversal or not if the operation has it, okay? And this is a matrix 3n by 3n, okay? Everybody understand that? So in principle, if you have a system, you can, and this set of matrices 3n by 3n for each operation of the parent space group is a representation of the group. But in general, of course, it will be reducible because it is a very big matrix. So the point that was explained yesterday is that what you do is decompose this set of matrices in small blocks, and you are able to do it for all operations of the parent space group. Sometimes when people hear about representations for the first time, they say, okay, why you don't diagonalize the matrix? You know what is the process of diagonalizing of a matrix. We learn it in basic physics about eigenvectors and so on and so on. The point is that you do not require to diagonalize a single matrix. You have to diagonalize all the matrices for all the operations of the group. And there is when you cannot diagonalize with only one by one blocks all the operations at the same time. And the only possibility is that you do smaller blocks, okay? And this is what we call decomposition into representations, irreducible representations. And this is a mathematical problem. It has nothing to do with physics. It is just something that can be done once you know all these matrices associated to the operations of the group, then it is a mathematical problem. It has nothing to do with physics. So let me summarize this here. You start with your very naive description of your distortion, and what you do is just try to find a basis combining all these bases which are, let's say, collective because they involve not a single atom, but they involve several ones. And by this means of a change of basis, you transform all the matrices into block forms, smaller blocks. But we have still the problem that n is infinite, okay? And the point here is more or less as Juan said yesterday, the block theorem. If you have a wave with a wave vector k, and you apply any transformation of the space group, you will finish in another wave with a wave vector, which the only possibility is that it is a rotated wave vector, but it's still a wave, and it's still a wave with a k vector which is related with the original one by a rotation. And that's what I tried to indicate here. I mean, the first block decomposition, it is into k vectors, okay? Each block here involves not only one single k, involves all the k vectors which are related between them by rotations of the parent space group. And how many blocks do I have here? Many. If n is infinite here, the number of blocks here is infinite also. But now it is a much simpler problem because the infinite has become, has been reduced to an infinite number of k vectors. And this, you remember, the number of non-equivalent k vectors is the bridging zone. I mean, you take the bridging zone, and there, if you apply periodical boundary conditions to your waves, you will have a finite number of k vectors inside the bridging zone, and this, but infinite. I mean, so big as the number of unit cells that you are including in your crystal. So now we have got rid of the problem of infinite. The infinite goes into your k vector. Once you have chosen your k vectors, now there is no infinite to consider. Now, in these smaller blocks where you have a set of k vectors which are related by rotations of the original parent phase, then it can be decomposed in smaller blocks. For instance, if the G operation keeps K1 invariant, then you will have a smaller block here because all the waves, all the operations that do not change the k vector just will transform your wave in another wave, but with the same k vector, okay? So you will have here a smaller block. And then if it changes K2 into K3, then you will have non-diagonal blocks just relating K2 with K3 and so on. And this is what, by means of equations, Juan showed you yesterday, okay? When he started to talk about k vectors and how you construct the blocks of a irreducible representation. And let's just go into this K1 here, and this K1, what is the size of this block? The size of this block is, I put here 3s times 3s. What is the s here? Number of magnetic atoms in the primitive unit cell. That's all. I mean, how many waves you have to combine to produce a distortion with a single k vector? If you have s atoms in your unit cell, you have to say this is the wave for atom 1, this is the wave for atom 2, this is the wave for atom 3, and nothing else. You remember the infinite has disappeared because you know once you have chosen a k vector, what happens in all unit cells is known if you know what is happening in your basic unit cell. And why 3? Because for each atom, you have 3 components, okay? So these blocks are 3s by 3s. And now this is the one that you have to decompose into irreducible representations corresponding to your parent space group. And what else I wanted to stress? Yes, and of course, the block, the irreducible representation, what we call the full irreducible representation, has to be considered this block, but also the ones that come out when you apply operations that relate K1 with K2 with K3 by rotations. Okay. So now let's come back and see if we have understood something. Remember, this was the first, I think, the first example that I put you the first day. I have a compound with the manganese at a Vico position 4b, which means it is, you go to the tables and you see what is this position for this Vico position. And from the experiment, I observed that the wave that I observe is 1/2 0 0, the famous K-search that you have been doing in some examples. And as Dimitri said, just try it by hand, just look if your diffraction data has this K-vector appearing in the Bragg peaks or not. So you know it. This is what you assume. And we know this 4 here in the Vico position means that you have 4 atoms per unit cell, per primitive unit cell. And now my question. Remember that we obtained this just without irreducible representations at all. I mean, these are the only thing that we were using here is let's look to all possibilities, all possible symmetries that come out if I know that the K-vector is 1/2 0 0 0. And what the program in the Bilbao server gave you or can give us is this, a list of space groups or magnetic space groups, and that you can see the hierarchy group subgroup between them. And so the minimum symmetry that you can have is this one here. What does it mean, this magnetic space group? It's very simple, nothing except what is forced by this exponential, by this wave. That it means from one unit cell to the next, you have to apply the wave construction, which means the next unit cell along X will be, the spins will be just opposite. The next one will be again the same, that one again opposite, okay? Because this exponential is the wave that we are observing just by saying that the K vector is this one here. Okay, so that the question is how many, if I could just make a model with this very low symmetry, with only forces this relation between the spins between unit cells, how many parameters, how many magnetic spin components I will have to determine? This is my question. If you don't know this, I'm afraid we are very far from understanding anything. So let's assume that I don't imagine I have no symmetry, and I look for a model by trial and error, just saying, okay, the only thing I know is that from one unit cell to the next one along A, I have opposite spins. The next one, I have opposite spins, and so on. I mean, plus, minus, plus, minus. How many parameters I will have to use in full prof to determine this model? Anybody can raise? Nobody knows that? You have 4 atoms per unit cell, and the only thing that you know and that you are forcing is that from one unit cell to the next one along A, the spins are opposite. And you have 4 atoms, magnetic atoms per unit cell. So how many parameters do I need to describe this model? 12. 12, okay? So without knowing anything, if I go to the tools in the and I produce, remember that we could produce with the tools that in the Bilbao server, I have produced exactly the model for this the lowest symmetry. So you have it here. I'm going to, you see, as the symmetry, we don't have any symmetry within the unit cell. The asymmetric unit includes all the atoms in the in the unit cell, because I'm not relating between them. And in the loop of indicates the magnetic atoms, I have to put the 4 atoms, okay? And here it indicates that the 3 components are free, okay? So number of parameters, 3 times 4, 12, okay? I will have to determine all the values of all that are 0 now here in the starting model, okay? Good. So now, what we do when we just force some symmetry here is to reduce the parameters. Just saying, okay, this atom is related by symmetry with this atom and with this atom. So if I know the magnetic moment of this atom, I will know the magnetic moments of the other ones. And therefore, the number of parameters start to decrease, okay? If I go from here, sorry, let me just come back here. If I from here to higher symmetries. Everybody understands that, okay? So we are just, by saying, I'm going to make a model in this symmetry group or in this other symmetry group, what I'm doing is just the simple thing of saying not all the magnetic moments are independent, not all the atomic positions are independent, so let's try it and the number of parameters will be smaller. So now if we go to the magnetic representation of this K here, okay, the first thing that we should know is that this K has no additional K vector rotating by the operations of the parent space group, because the parent space group is orthorhombic, so it only changes X into minus X, or Y into minus Y, or Z into minus Z. It does not mix X and Y and Z. And it means that the only possible rotated K vector that I could have is minus 1/2, 0, 0. But minus 1/2, 0, 0 is equivalent to 1/2, 0, 0 by a reciprocal lattice translation. So what we call the star of K vectors of the representations, it's a single K vector in this case. So from these blocks that we talked about, there is only one K to consider. And the magnetic representation for this K, what is the dimension? We said it will be reducible in general, and it will be, we said that we had 12 magnetic components if we had no symmetry. So it means that if I apply a transformation in general, I mean an operation of the parent space group, I will have a matrix 12 by 12, okay? That's the point. I mean, my representation is not anymore infinite, it's only dimension 12. And now I'm going to show you a very simple program that in the Bilbao server, which is this magnetic representation, which says the composition of the magnetic representation into reps. So if I go here, I put my parent symmetry group, and here I put my wave vector, which is 1/2, 0, 0, 0, and I submit. The first thing that appears is the list of possible positions that my magnetic atom will have, or my magnetic atoms. You may have several ones. You can choose several ones if you have several ones. But here, the position is 4B, so I click on 4B, I submit. And this is the result. It tells me that this the composition of my representation, which we said is 12 by 12, is decomposed in 3 times an irrep which is called mx1 and another 3 times mx2. This is fully equivalent to what Juan showed you yesterday with basireps. If you use basireps and you use not the old option but the new one using the labels of the isodistort or isotropy, which are this, what we call CDML irrep nomenclature, then you will see that it's exactly the same result. So what is telling me this equation? That's what you have to understand. It's telling me that this 12 by 12 space can be decomposed into two different, into 2 subspaces, each of them of dimension 6, okay? The parenthesis here, this 2 here, means the dimension of the rep. I mean, they are matrices 2 by 2. And the 3 means that it's repeated 3 times. So I have 3 blocks of 2 by 2. That means it's a subspace of 6 dimensions, okay? That corresponds to this rep mx1. And the same thing for mx2. If you are curious what is this mx1, mx2, you can go to here, no, here, sorry, to another section here which says representations and applications, and here for point and space groups, and in our case are space groups, so I go to representation of space groups, and here I choose my space group, 62, I submit, and here is my k vector, 1/2, 0, 0, 0. Here it gives the list of all possible k vectors in your Brillouin zone. And you can use this list instead of this complicated list that Dimitri showed the other day. Here you have the full set of possible k vectors that you could try, for instance, when you use when you search the propagation vector manually. Here it is the one that sorry, what I did, x, so I choose x, I submit, and here you have it. This the x1, x2, and in our case it appears mx1, mx2. Why? Because we distinguish that these are magnetic irreps. That means here there will be the list only of a space group, and you remember that when you go into the great group, all the operations are duplicated, and if I say mx1 means that all the operations with prime, which include time reversal, just are odd for time reversal. That means that you take these matrices and you just multiply by -1, and this will be the matrices for the operations including time reversal. But the point is that you have perfectly defined the irreps, and you have only 2, in fact. And you see, Dimitri, here you have 2-dimensional irreps, even if it's orthorhombic. So you may have more complicated irreps than just 1 - 1 one-dimensional irreps, okay, which are the simplest one. So let me go back then to where we were here. So again, so that's what I just showed you, and just this is the labels are the same that you can find in the isotropy web page, and that you can find also in basireps if you use the most recent options that Juan explained yesterday. So that's our result for the moment, that we have 2 IREPs and so on. And now it comes Landau theory. Landau theory says if the transition is continuous, a structural one or a magnetic one, then the distortion should transform according to a single irreducible representation. That means that these 12 by 12 matrices, I know that in the simplest cases, when the transition is continuous, then instead of being 12 by 12, it's going to be, which dimension is going to be the one corresponding to my distortion? If it corresponds to a single IREP, remember, if I divide my space of 12 dimensions into IREPs, I divide it into 2 subspaces of 6 dimensions, okay? So the matrix, instead of being 12 by 12, is now 6 by 6, okay? So I reduce the number of the representation into not a single irreducible representation, but 3 times repeated mx1 or mx2, okay? And the point is that even if the transition is not continuous, which is in most of the cases, then this assumption works very, very nicely. And even in the case that it is broken by the fact that only a few number of irreducible representations are involved. In fact, the fact that we see in my diffraction data a single K or only a couple of propagation vectors, and this is part of this assumption of Landau, because seeing only a single K means to reduce the number of possible irreducible representations to those that corresponds to this K. And you have seen that this is reducing the big number of possibilities that I have to a single K. So this is the basis of the representation method that is being used for decades to modelize and to modeling the magnetic structures and try different models. Because the first thing that you do is saying, okay, let's try a model according to a single, that the distortion, the magnetic ordering, transforms according to a single irreducible representation. So let me be clear. If I just say, okay, let's try models according to mx1, it means that I will have, instead of 12 parameters, I will have 6 parameters to determine, okay? 6. And this is what BASIREPS does. When BASIREPS gives you what is the basis modes for one representation from the other one. And it will give you 6 basis modes that you will have to fit to your data, the amplitudes of these 6 modes. And here I try to just make clear that this idea of IREPs is mathematical. They do not depend on your specific system, and you do not need to calculate these IREPs, but you need to know how to use them and what they mean. And this was the approach I said that in the 60s was promoted by Dato in Grenoble, and there was this some kind of competition saying, okay, you see here in the abstract of this review paper, the superiority of representation theory over symmetry invariance under Shumnikov groups. So this method was presented as an alternative to the use of magnetic space groups. And in my view, this was a big error. I mean, because they don't have to compete, or they are not alternatives to approach a magnetic ordering. They are just complementary. They are different informations. The point that this approach could be used also for incommensurate structures was very strong. I mean, because at this time, superspace groups were not known. They have not been invented, let's say, or discovered. And this means a big advantage with respect to using Shubnikov groups, because you could also use the same approach for incommensurate structures. And the point is that very soon appears software that apply this approach. And the point is that this system of saying, okay, these are two alternative methods and one is superior to the other one, so people in general forgot about magnetic space groups, and they just used the representations, and they even did not assign a space group symmetry or to their model, or even a point group symmetry. Here I want to just show you that we have just very recently published, Juan and myself, a paper where we tried in a very brief way to tell you this relation between magnetic space groups and representation analysis, and how in the end, now with the tools that we have available then both approaches can be done, or can be used, as Juan showed you yesterday, perfectly together, and not as alternatives. So that's why in the section 3 you have a section saying how representation analysis and magnetic space groups work together. So this is the point. The problem of just saying, okay, my point I want to say, do not approach representation analysis as an alternative to magnetic space groups. They are not just methods. They are different things to approach and to describe a magnetic ordering or a magnetic structure. They are just fully equivalent if the representation is one-dimensional. That's what Francois just stressed yesterday, and that's what I put here. Only in the case of one-dimensional IREPs, there is a one-to-one relation. You have IREP, and the IREP corresponds to a single magnetic space group. But in general, if the IREP is more complicated, like in this case, then you may have several magnetic space groups for the same IREP. So, this is my message, and here you have a tutorial that you can download from the Bilbao server, where all this is more or less, with some examples, explained and described. But let's go back to our example. Remember, this was the real case for this compound. This is and we said, if you try maximal symmetries, you are very probable that you find your structure. But if we go back to well, the first thing that I went to K-subgroups MAC, okay, which is the one with which I constructed this figure, this graph of subgroups, and I'm going to try to reproduce the same thing. 62 for the parent space group, 1/2, and let me stress this possibility that you have here. Show the independent vectors of the star, okay? If you click here, the program will tell you if there are other wave vectors which are symmetry related with the one that you have observed. In this case, you see there is none, okay? It has not increased the number of K vectors, but let me go back and just put here one-fourth 0, okay? And show the independent vectors of the star again. Oh, no. Well, here it does not include, in fact, there are two, but you see this comment here. In those cases where the pair of vectors k and minus k belong to the same star, they are not listed, okay? But in more complicated cases, let's say, like a trigonal one, okay? And I put here 1/2. And so here you see that the star has 3 vectors. I want to stress this because Dimitri is going to talk about multi-K structures afterwards, and that this means that when in your structure in powder diffraction you have indexed all your peaks with 1/2 0 0, it does not mean that your structure is for sure single K. There can be solutions where also these K vectors are involved. And traditionally the approach is, okay, the simplest thing is to assume a single K arrangement, but there may be good reasons to assume or to propose models where only if you have index with this K vector, you can also include this one and this one in your model. And the symmetry, the magnetic space group that will correspond to your magnetic structure will be completely different. And the number of parameters that you have to determine and so on will be completely different. Well, but what we wanted to do is to put here 62, okay, I will do it here, 1/2 0 0. Oh, yes.
So is this equivalent K vector related to just what we got in different domain, or in different domain, magnetic domain, symmetry related magnetic domain, or no?
If you have single K structure,
yes,
then some operations lost will go from your K vector to the other 2 vectors that I show you there. I mean, you will have domains with this K vector, with the other one, or with the other one.
I see.
If you assume a multi-K structure where all the 3 of them are involved, this operation that rotates from K1 to K2, K3, maybe is not lost, okay? So we'll not have, the number of domains will be completely different. And this is the problem, because even if you have a single crystal, you will have, you will see the peaks corresponding to the 3K vectors, and you will not know if these are domains,
yes,
or it is a single phase showing this. Maybe Dimitri will talk about this afterwards.
Okay.
So the point is, yes, if a multi-K model and a single K model, the difference is completely different with respect to the possible domains. Because in the case of single K, the different K vectors will correspond, these 3 vectors will correspond to different domains. While in the multi-K structure, they will be all together in the same structure, in a single domain.
Okay, thank you.
So, we were here, we go to submit this, we have the list, we have the graph. Remember that the approach to do in practice for refinement, you click here, the models that you want to try in your refinement, you go here and you submit to MacModelize and you produce the MC file for the models that you want to try. But what I want to show you now is that there is a very nice feature in the program which says, okay, this is the figure that I've shown you. But if I go back here, here, and go to this option here which says show only subgroups that can be the result of a Landau type transition. So if I click here, then, and I submit, the list is much smaller because now it's forcing that this model and this symmetry is produced by a single irreducible representation. And if I look it in a graphical way, the number of possibilities has decreased. But it has not decreased to 2. It has decreased to 6. Okay? And I want to just to explain you why this is happening. So this is what we have, and so we had, remember, a decomposition into 6-dimensional subspaces, one or the other. And it means that if you go to BASIREPS or SARA or any program that is using irreducible representations, as I said, it will tell you, okay, you have 6 parameters to determine in your refinement because you have 6 basis vectors. But if I go to the MC file for this solution here, it will have only 3 parameters to determine, not 6. So, and instead of having 2 possibilities in using IREPs that says, okay, the solution is either of this IREP or this IREP, here you have 6 possible solutions for your symmetry, let's say. And, well, this I will, and why it's happening this? I mean, this is happening because once you are in a single irreducible representation, as our representation is 2 by 2, then there are, depending on the orientation of this Q vector, which will be 2-dimensional, it will be kept, and it means that this operation is maintained. It's part of the magnetic space group, and other operations will transform it in a different vector, and these ones will be lost. Because, so you go, as I tried to show here, this is one vector, and some operation takes you here, and some other operation takes you here. These are the domains, okay, in the energy map. And the operations that do not change this direction, these will be the ones that are maintained. And this Q here is what we call order parameter, which is the term invented by Landau. In general, this is what we call the invariance equation. You have your matrix of your IREP and the vector that you are saying, okay, my distortion, it's a n-dimensional distortion that according, if I apply this operation, is transformed in general in a different vector, but if it is maintained, then this operation is conserved in the magnetic arrangement. And the point is that the operations that are kept depend on the direction that you take. This is an example. Let's imagine that you have an operation where the rep, you've seen the matrices 2 by 2 that the Bilbao server can show you that corresponds to this rep. And then you take this matrix 2 by 2, you apply to a vector which is in the direction 1, 1, and it will be maintained. But if you take it in a direction A, 0, it will be lost, okay? So it means in order to maintain some operations in the magnetic space group, you have to combine your basis vectors that BASIREPS gives you in a very special way. That's what Juan explained yesterday. And this way to combine them to produce some, to maintain or to conserve some particular operations, if you use basic reps, you cannot control it. You don't know. But if, and let me show you again, if we go to the, so I suppose I'm, here again to our list of operations, okay? Where is it? Here. So let me see the list of, and I think I do it for this one, okay? So this one. Here you have a column where it says Getty reps, okay, for this particular symmetry, okay. And the program just, this is the input, so what I'm entering is just my parent space group and the symmetry break into the subgroup defined not only by the type, but remember, you have to define the subgroup indicating the transformation matrix to standard. So this is only just the input that the program, which is a standalone program also in the server, but in this case, you have a direct link from K-subgroups Mac for this particular symmetry break. And here is the output. And the output says, okay, this symmetry corresponds to the rep MX1, okay? But here it indicates what particular direction of the order parameter must have in order to produce this particular magnetic space group. So it is not AB. If it would be a completely arbitrary direction, it will be AB. But here it says AA. It means you have to combine the pairs of basis vectors of your program that has described your basis vector. You have to combine in a very particular way the basis vector 1 with the basis vector 2, the basis vector 1 to the basis vector 2. So in fact, you don't have 6 parameters anymore. You only have 3 parameters. So always that you have a special direction, and here you have, then instead of having 2 degrees of freedom, you have a single degree of freedom. You are not free anymore to move around in a space of 2 dimensions. So the number of parameters that I expect to have here, it is not 6, it is 3. If you go to the MC file, you will see that in fact the number of parameters to refine is 3. If we do the same thing, so this is what we have obtained. If we do the same thing for the low symmetry group, which is below, and which is a subgroup of the, you will see then that the rep is the same one, but now the direction is arbitrary. So, and here, this is what we call the isotropy subgroup that was mentioned by Dimitri the other day. And these are the isotropy subgroups for this. What are these reps here? These reps are, do not have M, so they are not magnetic. They are the structural ones. They correspond to displacive modes that can appear, or even strain also, or something like this, and which are allowed because once you lower the symmetry to this one here, then it means anything that is allowed by this symmetry will be free to be present in your structure. And what this table is telling me is that apart from the an arrangement according to mx1 for the spins, I may have some structural distortions according to these structural modes, okay? Okay. Okay. Let me show you finally that you can use the program and filter by reps, okay? So if you filter by reps, you can do it, well, I will not have time, so I will not show it on real time. You will say, okay, I want all the possibilities, all the possible symmetries for mx1, and this is what you obtain from the program. It gives you two possible, what we call epikernels, and the kernel. This is the one, the model with 6 parameters, the one where you will work if you just combine the 6 basis vectors that the program doing the analysis, the representation analysis method. And these are the models with different symmetries, which alternative symmetries that can happen with when you combine the basis vector in a particular place. But the point is that once you decide, okay, let's try this model or this model here, you don't have to worry about the reps anymore, okay? You just say, okay, let's try one of these models. So if we go back to the graph that we have obtained with the Landau condition, you remember, these 3 possibilities correspond to one E-rep, and these 3 possibilities to the other one. And this is the final result. If you make the model according to one of these high symmetry or epikernels of one E-rep, then you have here, you see the 3 parameters, which are the 3 components of your single independent manganese. And these are 0 according to the experiment, but you know that they are not symmetry forced. They can still, you are still in the E-rep if you just in the rep and constrained to this particular symmetry group. Let me show you here that in the case that the E-rep is 4-dimensional, for instance, for this case, which was one of the examples also on Monday, you have many possibilities, many different magnetic space groups for the same E-rep. That means you have many different, and one of them corresponds to the report of the magnetic structure. So you have 13 distinct epikernels for the same E-rep. So I think this can be enough to convince you that E-reps and magnetic space groups are 2 different things, and they can be combined together. I don't have time to show you that things may be more complicated, but you can read them in this paper or in the guidelines that have been mentioned before. But let me show you what is the difference. The difference here is that if you apply the Landau option of the program, it will give you a graph like this. These are the possible symmetries if your E-rep is 1-dimensional. You remember there is a 1-to-1 correspondence between a magnetic symmetry and an E-rep. So you can work perfectly okay with this. But in the case of 2-dimensional E-reps, which are possible here for k equals 0, then you have different symmetries, and the difference is that now you have what we call secondary reps. Juan yesterday showed you a case where you had this secondary rep. That means it's not the one that produces the magnetic ordering, it is not the one that drives your magnetic ordering, but according to the magnetic symmetry group, it tells you this rep can be also important or can appear as through coupling with your primary order parameter. So this is what I wanted to show. And And finally, this is, for this particular case, something similar to what Juan showed you, but I want to stress what is the point, that you can use full prof combining both. You're saying, okay, I'm going to make a model according to this magnetic space group, and within this magnetic space group, I'm going to restrict to a particular IREP. In this particular case where you have several IREPs, not in the first example that I showed you, there was a single IREP, so there was nothing that the IREP could add. But here, yes, because you have a secondary IREP, and here is the list. This is, for instance, the definition in the PCR file of mode 2 according to M gamma 6 plus. It's rather different of how you define the basis function of an IREP in bus IREPs. It's completely different because you are only indicating what happens to the two atoms which are symmetry independent in your asymmetric unit. In principle, these two atoms are independent, but if you say, no, I want a model with mode 2, according to mode 2 of this IREP, it's telling me, okay, you move the moment of along the component along mx, and the component along my will be one double of the other. You see these two numbers, they are related by a factor 2. And again here, mode 3 is a factor 2 between this one and this one. And what happens with the spins of the other magnetic atoms in the unit cell, it is something that it's taken care by the magnetic space group. You don't have not to care what happens with the, remember, in the unit cell there are 4 atoms. No, in this case there are 6, in fact. So in the end, you have 3 parameters here to refine. One, you know, corresponds to a secondary IREP, which you can, in principle, you can expect that will be negligible because it's not part of the primary order parameter. So in fact, in the end, you have to refine only two parameters. And, well, I think you can review. You have the copies, the PDF of this, and you have questions, just you can ask me. Thank you very much.
Alden, I think we will go to next. Thank you, Mato, again.